As silly as these steps may be, I feel they really organize your process of drawing and allow you to draw out a chair pretty quickly and easily. Because you will find that you get some instructors that do something annoying like that, which is awesome. They just drew a chair in one fluid move that doesn't look too horrible, and we can apply everything off of it. The issue with that is that if I tried to do the same thing with the other chair, that one actually doesn't look too bad, but it starts to blur and get a little bit wonky looking. You will find one of your chairs is always drawn better than the other. Okay? If you can come up with a method to keep your chair drawings as organized as possible, the better off you will be. That's what this procedure is designed to do. Start with a seat. Okay? So our seat, in this case, our chair will end up aiming towards the left. If I wanted to draw the chair, that's right. I'm going to write that down, just in case somebody else misses that. It's kind of a joke. Chair aim, you didn't have to laugh. Chair aim the other direction. We'd stagger it the other way. Hopefully I can stagger it properly. Okay, and now our chair would be aimed that way, which is aiming to the left. If we cut it roughly, the middle of the overall structure, okay, I can pick the left or the right side of that middle dashed line area. It doesn't really matter. I'm going to pick with the left side. Okay. Whichever line is shorter, I will draw an up or draw in that direction. So if we look at the left side of the right-facing chair, because that's not confusing, okay, the top line is the shorter line on the left-hand side, so I will draw up. Okay. Step 3, complete the triangle. Okay, I will then repeat on the other side, and I now have a chair. Relatively beautiful, relatively painless, and nicely set up. If we go through and do it on the other side, short was on the bottom, so I'll draw down. Short is on the top, so I'll draw up, and I'll complete my chair. The reasoning for a lot of this has to do with getting the angles right so that they match up. The hardest angle I've found to nail down is the one and kind of the upper part of the chair. That is a hard angle to draw appropriately. This method seems to simplify that and nail that down pretty well. Okay? Questions about how we draw chairs?
Where's the head?
I will get to that. Any other questions about what I've got drawn here? Okay, so let's take a look at identifying heads, feet, and all that fun thing for referencing. If I was going to draw a little person, there's my little head, my little smiley face. Everybody made fun of my drawings before, so you can make fun of them again. It's not like I have feelings or anything. His other arm is by his side. You can't see it. That's not going to be good. That's too good. His other arm is by... Crap. If we look at the other chair, if he was to sit in that, there's a little smiley face dude. He's waving to his buddy on the other side. He's making him the sick-fingered man. And they can now sit and wave at each other. So what we're trying to identify are the different pieces of our chair. And everybody's going, oh, that's an ugly-looking chair. Yeah, it doesn't have to be perfect. Okay, so our head is the red atom, or the red atoms on our leftmost chair. Okay. The feet would be the blue bonds. And the seat would then be our black ones running through the middle, on the leftmost. Okay. This means that these atoms are all in front when we're looking at our chair. Okay? That's the side of the chair closest to you as the observer. Okay? the atoms not highlighted over in purple are furthest from you. The head and the feet atoms, the ones forming those points, are by definition in the plane of the drawing. Okay? The next fun part, are there other chairs? Absolutely. Okay? You can look at an individual chair and find at least two other orientations of chairs. Okay? If you don't want to see those orientations of chairs, feel free to close your eyes and ignore this part. We have a chair facing kind of out at an angle away from us. We also have a chair aiming back behind the plane of the board. Okay? Don't look yet if you didn't want to see that. Now you can open your eyes again. Those chairs are erased. Okay? The idea behind looking at our chair in this one fashion is that allows us to then be uniform across all interpretations and make sure that we're always referencing the same thing. Okay? You'll then hear a reference to something known as a chair flip or a ring flip. And I think it's only those two words. Okay? What is happening within that is we are exchanging the head. Okay? We're taking the head of our chair and we're pulling it downwards to make it feet. Okay? We're taking where we had our feet, which I wrote as blue, that was supposed to say feet. Taking our feet and we are pulling that upwards to make it a new head. Okay? That is the chair flip or the ring flip. Okay? The reason why I'm addressing this is what is happening in the process of doing a chair flip. And don't tell me it's ring flipping. What's that? I don't quite accept changing the position. Rotating. Rotating I'll accept. What's rotating? The sigma bonds. We're doing a rotation within the bonds. The atoms are really kind of staying in their same general area, their zone, if you will. Okay? And all that's happening is we're rotating about a single bond. We're not rotating the whole structure. Okay? It is very common for students to go through, sorry, I just want to make sure we're still recording, and take the whole chair, and I don't have enough space to draw this, so I'm just going to gesture, is take the whole chair and flip it over. Say, well, that is a flip. Okay? The issue with doing that is that you took the little dude that was sitting happily in the chair and you've now smashed his face into the ground. That's not a good thing. Okay? The idea is that you just make him turn around. Okay? No face smashing. Okay? What do we mean by turn around? If we take a look at our chair, the head became the feet. Look at our other chair on the right that was facing to the left. The red bonds that were our head now are our feet. The blue bonds that were our feet have become the head. That is a ring flip. That is how you would draw it appropriately. Kind of makes sense? Okay. I'm about to erase everything. Are there questions? Yes?
Does that change which bonds over on the other side are at you or not?
That does not change the atoms being at you or away from you. Okay? And that's one of the confusing aspects. It's a good question. Okay? Our head is still that red atom down here, that red point. Still that blue point up there. Which means the ones coming at us are still these. Okay? Most students have a hard time with that because it sure looks like we didn't just do a chair flip, we also did a rotation. No, all we did was the chair flip. There's no rotation associated with this. Okay? And that becomes relevant when you're trying to nail down multiple choice answers, because if we say, do a chair flip on this structure, which of these is the appropriate answer? More than likely what we've done is a chair flip and thrown in a rotation. By doing both of those in the answer choice, it forces you to be aware of your three-dimensional spatial awareness and really understand what's happening within the model. Okay? Because one of the answer choices will very likely be very, very similar. It'll probably be the mirror image. Okay? You might say, well, that's not a big deal. Are my right and left hand interchangeable? No. Okay? They are not the same thing. Same thing's going to happen with the structure. The structure that we would pick for a chair flip is one that has a mirror image, very similar to my right versus my left hands. They're non-superimposable. It's a different structure, which then means you have a tendency of selecting that different structure because we'd orient that one in such a way that it sure looked like that was the answer. Okay? So be very careful with what you're choosing and looking at within your structures. Particularly within this unit, you have to be very, very particular. Okay? One quick and easy way to avoid all of that kind of particularity, use a model kit because you're allowed to. Build the model. Does it match the drawing? If it doesn't, that's not your answer. Okay? Other questions? Okay. Sorry. Let's draw this a little bit bigger. Doesn't have to be perfect, but it's pretty close. All right, now what we're going to do is address an interesting point, which is I thought where Brian was going. Let's draw on a couple bonds. Let's draw on that bond and then that bond. Would we expect those bonds to be the same? Okay. For those of you not in lab, this is really a question aimed at you, because those of you in lab already know the answer because you've already worked with this a couple times. The purple versus the green, are those the same energy? Okay, they will not be the same energy, and it's not inherently obvious from the drawing, and it might require a little bit of practice to get used to it, and that's what the next few slides are going to be looking at. Okay? Because they are different, we will name them differently. The purple one we'll call purpley. Joke, axial. The green ones we'll call, I know I'm not funny, it's okay. The green ones we'll call equatorial. And this has to do with where those atoms are aimed relative to the ring. That purple one is aimed where? Up from the ring. The green one's aimed kind of out away from the ring. Okay? It's easiest to see at that point. We could also draw it on the other point. Got one there and one there.
Are we allowed to just simplify and just say EQ?
We'll address that in just a second. Okay. The purple one is still axial. The green one is still equatorial. Okay. Which I'm simplifying as AX and EQ for the moment. Okay. Notice that the equatorial one is always kind of out from the structure. The axial one is either up or down. Right? It's on the axis of the structure, hence we call it axial. And the green one is kind of on the same plane as the atoms of our ring. That's our equatorial. Okay? The next part is addressing how do we draw those, because invariably I will get somebody doing this, the black line. Well, what was that black line? Is that axial or is that equatorial? I have no clue either. Okay? When you draw it like that, I end up having to guess at what you're trying to draw. If I'm guessing, more than likely, you're getting it wrong, because that's where I have to err on. Okay? So it might be nice to know how we should draw these. Well, we already started to address how we could draw the axial. Where are the axial drawn? Up and down. So what if I drew this? Is that one axial? No, it's not. There's an extra piece of information that goes along with our axial. Not only is it up and down, but it's up and down, and this is where it's going to get weird, in the direction of our triangle or point. So let's take a look at that lower right. The red atoms are conveniently showing us our triangle. Where is that triangle pointing? pointing down. So where's the axial? Straight down from that point. The blue triangle, largely pointing up, which means the axial is straight up from that point. Okay, let's look at a blue-black intersect. Where is that largely pointing? Down. Okay, which would suggest our axial needs to be down. Another blue-black intersection point. Where is that pointing? Okay. Again, our triangle is pointing down. There's the axial. You'll typically see people draw a broken line because that black bond is in front. It's a spatial thing. Okay. Does anybody not see this? Really? Okay. That one? Okay, so here are all our axials. Here's the fun one. I'm going to regret drawing it right there, but I'm going to do it anyway. So what's our equatorial? It's not, well, there's a lot of range within not axial. It might be nice if we could come up with a consistent pattern. Because if we go through and look at that black line, then we might say, well, that's equatorial because it's not shown as the axial. Okay? So it's not only not axial, it is, this is where it gets fun, parallel to the second bond. Taking the second bond away. So if we go through and look at that red point, I have 1, 2 bonds. Where's the green line parallel to? Well, it's parallel to that second bond. But the trick is that I counted only counterclockwise, and I should have gone clockwise. What would happen then? Well, 1, 2, oh, it's also parallel. If you drew your chair right, guess what? These rules will always work. If you didn't draw your chair right, you're making a mess of everything, and that then throws in all sorts of issues when it comes to grading. Okay, so let's clean that up, and let's draw in our equatorials. If we were going counterclockwise, that upper green dot, where's the equatorial position? Parallel to the second bond would be this one. So I will usually get students drawing this. What's the problem with that? Rule number 1 was not axial. And axial is aimed up. So where should the green one be aimed?
Down, right, down, left.
Down. Okay. The next one. Parallel to the second bond would be this bond. Okay, I can't draw it down, so I have to draw up. Does that start to look like it's hitting that axial position because it's going on that up-down axis? Yes, visually it's doing that. But remember, this is a three-dimensional model. Okay, we have to lose or use some of that information. The other equatorial positions. Okay. Patterns that come out of this. Every other up atom is... Every other up atom can't be down. Axial or equatorial. Okay. If we go through and look at this, we could say every other up atom was axial. So there's an up atom, skip, up atom, skip, up atom. Okay. But what if I had actually started over here? Well, what's the up atom at that blue dot now? Okay. That one becomes easier to look at within the drawing. The equatorial one is aimed up. But if you look at some of your models, it may not be easy to see that the equatorial is aimed up at that position. Okay. Typically, it is classically very difficult to distinguish where the equatorial atom is aimed. So just remember that the equatorial is not axial. The axials are easy. So identify the axial. Guess what the equatorial is? The opposite of it. Okay? And that allows you to go through and identify and find those positions relatively quickly, okay, with, of course, some difficulty, but it at least simplifies it. The hardest part is being able to draw these. If you can't draw them right, you won't be able to answer any questions. We good? Okay. So, different chair energies. How do we determine the energies in different drawings? What drawing allows us to visualize that energy? Chair technically doesn't give us energy. We could just see that they were different. What are you talking about? The circle and the Y, the dot, you mean Newman projections. Okay? With our butanes, all that fun stuff. Okay? We can do that again with the chairs. The problem with that? If we were to go through and look at a chair to identify our Newman projection, what we'll find is that there are two Newman projections that are fused to each other. Okay? And this is where most of the lab people are going, yeah, I know, that sucked. I still don't even remember what was going on with that. Okay? It is challenging to nail this down. Okay? I think it's important, which is why I made the lab do it. The lesson that really comes out of looking at your Newman projections comes down to the different energies when we're looking at our equatorial and our axial. I notice the equatorial I've got labeled here as E and the axial as A. What happens if I do a chair flip? Okay. Where's the chair in this? This is even harder. If you sat in this chair, your back would be facing us. You'd be facing behind the board. Okay? Here's the back. The seat is actually where we're looking through our Newman projection, and there's our footrest on the other end. If we go through a chair flip, what has to happen? The back needs to come down, and the feet needs to go up. If we were to go through and deal with our model kit and do that, what we should have ended up with was this drawing. We froze everything in location. Notice the labels went all sorts of wonky on us. Okay, why would they go a little bit wonky on us? What happened to the red E? It became axial. It's no longer equatorial. By going through a chair flip, it has changed its configuration, okay, or its conformation. It is now axial. What happened to the blue A? It became equatorial. For those of you saying, well, I can't see that at all, that's because this is a two-dimensional representation, and you should really use the model kit to see how the sigma bonds force those rotations to occur. Okay? That is why we have model kits. The lesson that's going to come out of this is going to come back to this kind of last things. Oh, stupid mother effing typos. Whoever made these slides, when I get my hands on them. The lowest energy place, we will place where? Okay, well, we have equatorial, axial. Let's try to elaborate and determine what's going on with those. Okay, so let's take a look at our leftmost chair. Let's keep our focus over here. There's our equatorial position. I want to know what it sees in the Newman projection. And I can't see anything with the Newman projection because it's too confusing. Well, what if I erase all of that? Does that help you? Staggered. Notice the bonds do not overlap, so it is staggered, okay, as opposed to eclipsed. So you should be able to see that. Okay, but as soon as we have a staggered configuration, what do we then need to look for? Emmanuel, gauche? Gauche versus anti. Okay, the gauche interactions would be that E with, whoa, that's an eraser. That didn't get any better. Would be that E with the hydrogen or that E with that hydrogen. Okay? Am I ever going to be able to remove the gauche interaction with the hydrogens? No. There isn't anything I can do about it. Okay? But because I can't do anything about it, it's roughly consistent in all cases, and it's relatively small, which means two people are running at you, a mouse and an elephant. Which one are you concerned about? The elephant. You probably ignored the mouse. Why? It's too small. And when we're looking at those small interactions, we can avoid it. You probably stepped on the mouse to avoid the elephant. Okay? The small interactions we can assume to be negligible, at least for our purposes in this class, and we can ignore that. Okay? What other interaction do we have in this? We have the anti-arrangement all the way around. Some people will reference that purple carbon. That purple carbon has no effect on the energy because it's connected to the exact same carbon as our E atom is, which means, what is the bond angle? 109.5. It's a tetrahedral carbon. The bond angle between E and our red circle would then be 180. It's a little bit weird to reference that, but if we assume flat 180, that is an anti-configuration. Okay? That configuration we'll look at because we're looking at our E, a large group, and our carbon as a large group. We want to know where our large groups are relative to each other. Well, they're as far away from each other as possible in this configuration, so I can remember that as the anti, and I'll go through and label that. We have an anti-arrangement for the E. What happens for the blue one? Well, we can kind of cross our eyes or just eliminate the other half. Where's our interaction now with that A atom? We have the, and I am going to try my best to continue to pronounce this appropriately, gauche interaction. It's not going to stick, but I'm going to try. Our gauche interaction, right, with the methyl. I again have the hydrogen and I have an anti-hydrogen. I don't care about those because the hydrogens are relatively small. I'm going to refer to the methyl, okay, or our carbon. So I have a gauche interaction with A and I have an anti-interaction with E. Which interaction was lower in energy? The anti, which means E is in a more stable configuration than A. Okay? So given the choice, our lowest energy places is to place the largest group in the equatorial position. Yes, editing. Okay? What happens as we go through a chair flip? What happened to E, our red atom? It became axial, which is a gauche interaction, higher in energy, it's trying to repel away. What happened to our green atom? Okay. It became anti, it's now happy. So with this molecule, what's going to happen? Well, our ring is going to be constantly oscillating back and forth between these two configurations. Okay. Our leftmost structure, A, is going to be interacting with the ring to bounce away from it to force the rightmost structure. But as soon as I form the rightmost structure, what does the red atom do? Bounce away from the ring to shuttle us back to the other one. And so we are in an equilibrium between these two configurations. Okay. Could we predict which equilibrium is more favored than the other, or which side is more favored? Okay. What's that? No? If we knew what A and E were. Let's call A, that's the wrong eraser, a CH3. That was a horrible color choice. Let's try that again. And let's call E carbon, CH3, CH3, CH3. Would I expect the leftmost structure to win or the rightmost structure? Why the left? If I compare the blue atom, CH3 versus CH33, which one's bigger? CH33. The bigger atom wants to be in the equatorial position. That's in the leftmost structure. If it goes through a chair flip, what happens? becomes axial, which is higher in energy. So if this was my structure, most of the time it would be spinning in the leftmost structure here. Okay? What if I were to draw that in a chair configuration? I changed my mind. I'm not going to draw it. You're going to draw it. See what you got. You do it. See what you can come up with. Try and draw the chair configuration for that structure. How many people drew that as an answer? Yours is backwards. What do you mean? Is this structure what is drawn in the Newman projection? No. It's not even the same thing. Okay. It still has the CCH3 and it still has the CH3. The CH3 is still axial. The CCH3 is still equatorial. What happened? They aren't too close together. Left and right hands. Okay. This is that spatial awareness thing. Most people look at that and say, oh, that is the same answer. Isn't that valid? It's not. The answer that I've got drawn there is effectively the opposite hand of the actual answer. The actual answer is okay. Which brings up the next question. Could you have drawn the structure rotated? Yes. So in a testing situation, if I ask this question, it's a nightmare to grade because there's 50 billion different, there's not 50 billion, but there's a lot of different ways that you could have drawn the correct answer, different orientations. In fact, it would be, was it 6 different ways you could have oriented that molecule? What makes it even more fun is there's also 6 different ways you could have drawn the wrong answer that looks like the right answer. It sucks to grade. So typically it gets asked as multiple choice where I make you deal with that work instead of me. Okay? So be careful with looking at your structures and making sure you're permutating them correctly. How did I get the drawing that I've got shown here? Remember we said that this front atom here was the back. So what I did was take that structure and I kind of pulled it out and just turned it over, which means my back matches up. The CH3, which was in the plane in the front, ends up then being behind in the back. There's my axial. My methyl's up on the front hand side because of how I turned that structure. Okay? That spatial awareness takes practice. That's what the model kits are for. Make sense? Okay. Good, I recorded that. So here's the fun one. Let's turn it into a race. Left-hand side of the classroom can do the left-hand structures. Right-hand side of the classroom can do the right-hand structures. Okay? I want the overhead view and the chair view for both compounds. And we can make it interesting as 2 structures, 2 points, 3 points for either side of the classroom that gets their answers correct first. I kind of ignored the line angle, but we've seen the 2D overhead. This helps us with up and down because we can see the up and down as wedges and dashes. Okay, where the up, come on pen, where the up would be a wedge and our down would be the dash. We can look at kind of an implied 3-dimensional view with the chairs. Okay? And this really helps to elaborate axial and equatorial. We can also interpret up and down because it is a 3-dimensional drawing. Anything drawn, well, above happens to be up. Anything drawn below would be down. The axial and equatorial aren't necessarily just up or down. That comes from where they were drawn. So the equatorial at that position is up, but the equatorial at that position is down. So we have to be a little bit more careful when we apply up and down to axial and equatorial. Yes?
Actually, I have a question on the chairs.
The chairs up here? Okay. Give me a second, I gotta pause. Back to our other projections, we got our Newman projection. This is a 3D end view. The Newman projection really just tells us equatorial is more stable. That's our big conclusion out of it. Okay, so typically when we use Newman projections, it's just for our structures of butane or conformations of butane. We tend to ignore it for our rings. Largely because how many people see the ring easily in that? That's why we ignore it. Okay? There's one last projection that can potentially pop up, and that is known as a Haworth. Kind of hard to describe. I would really call it kind of a 2D side view, because we're looking at the two-dimensional overhead where we're assuming the ring is all flat, which it cannot be. Okay, but we're assuming it's all flat, but now we're taking it and we're kind of turning it on its side and looking at it from the edge. Okay? By doing so, this accents the up-down a little bit more than the wedges and dashes. Okay? And by accents, it means when we draw our line up, we know it's going up, and we draw it going down, we know it's going down, as opposed to knowing that a wedge is up and a dash is down. Okay? Just because I happen to logically just think of this. Any idea when the Haworth projections become more relevant? For biologists, because they can't comprehend the idea of wedge being up and dash being down, they need it to actually be drawn up, down to comprehend it. Probably a bit mean, but depending on what you're looking at, that it cleans it up. So I'll give them a little bit of credit there. Okay? Where that becomes really important would be something like this. Anybody know that compound? Yeah. It's sugar. Okay? It's sucrose. It's glucose and fructose. So it's a carbohydrate. Your carbohydrates tend to be shown in Haworth projections, largely, again, because biologists want an easier way to look at structures without having to understand organic chemistry, so they can pretend it didn't exist. Okay? It's there. We just simplify it. Okay? Baby steps. Make sense? Okay. So, text topics for your review. There are some questions in the smart work that pop up that I did not explicitly talk about in class because they're kind of definition things, and I don't really care because I'm not a definition guy. But I care enough that you at least read the textbook and are aware of what those terms are. So strain and energy, when we're bringing in numbers, you can get aspects known as angle strain, torsional strain, ring strain, bond strain, headache strain. Okay? There are different labels for how the different groups interact with each other. You technically need to be familiar with them, so I'm telling you that you need to read that section, and I had a homework question on it. Okay? But that's about as far as I'll test you on it. Your cycloalkanes, we did talk about the prop-but-pent shapes, okay, but we didn't go into a lot of detail with their different types of strains, so you should review that. Models, big deal. Constitutional as a word is referencing same thing as structural. I use them interchangeably. And then you'll hear this IHD. IHD is Index of Hydrogen Deficiency, which we will talk about in a little bit more depth in the next unit. It's also known as degrees of unsaturation. Any ideas why I might freak out at degrees of unsaturation or index of hydrogen deficiency? What does that look like? A formula or math. And yeah, not the greatest at that, which is why I tend to ignore it. I do not have that formula memorized, nor will I ever memorize that formula. Okay? It can be useful, but it's usually so meaninglessly useful that I would rather learn something useful that I could apply out than something that rarely has any use. Okay? But that's what this formula is. The easier out on this, a degree of unsaturation or one index of hydrogen deficiency is equal to a ring or a single pi bond. So if we have a triple bond, how many degrees of unsaturation do we have? 2, because there are 2 pi bonds. Not 3, because one of those is a sigma bond. So we have to be kind of careful with that assessment. Okay? If you're interested in dealing with that formula, we will again talk about it. The ring and pi bond equality thing works beautifully under most circumstances. Okay? With that, we are done with chapter 4. And with the last negative 30 seconds, we can talk about chapter 5.